Hello, everyone. Welcome to April talk in our seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 45-50 minutes, followed by time for questions and discussion. Please feel free to type your questions or comments at any time in the meeting chat. So it's my great pleasure to introduce our today's speaker, Professor Harald Helfgott from Paris University, France. Professor Harald Helfgott is leading mathematician who made fundamental contributions to number theory, group theory, additive combinatorics. He is widely known for his proof of ternary Goldbach conjecture, as well as for foundational contributions to the study of growth and expansion phenomena in groups. So in this talk, he will discuss growth and expansion in groups, including possibly progress towards celebrating Babai conjecture on the diameter of finite simple groups. So I'm now happy to hand over to our speaker.
Thank you very much. All right, so growth, expansion, and escape. I will be talking mostly about growth. I will talk a bit about expansion as one motivation. And escape is really for me a tool to, or a family of tools to get to prove growth. But what do I mean by growth? Well, let's first step back and talk about the basic objects we will be speaking about. So let G be a group, any group. Though we will be talking mostly about finite groups, many of the questions that we will be dealing with also make sense for infinite groups. So let G be a group and let A be a subset of G. We say that A generates G if you can write every element of G as a product of elements of A. So if every G can be written, element of G can be written as a word on the elements of A, we say that A generates G. Here, the AIs can be elements of A or of A inverse. That is, it can A inverse is just a set of inverses of elements of A. Very well. So now we have generation. We can define the Cayley graph. Now, if you have data set A generates a group G, I will define a graph that tells you will allow us to think of the structure of G and of A. So a graph, I don't mean a graph as in the plot of a function, I mean the graph as in combinatorics. So a graph is a pair, very formally, a graph is a pair, an ordered pair of consisting of two sets, V and E. E, so E is just a subset of V Cartesian product V. Of course, that's very formal. And many of us really think of graphs as being considered being made out of dots called vertices and edges or arrows joining them. That's perfectly fine. It's just like saying, a triangle is really a set of 3 points on the plane. And then when I actually have a piece of chalk and I draw a triangle, that's not really a triangle, that's a picture of a triangle or a drawing of a triangle. And the triangle exists in the world of ideas. So it's a bit like that. So here's the graph exists in the world of ideas. It's a set V and a subset of V cross V. And if I draw a nice graph, say this would be a complete graph, it looks a bit, actually it is a satanic symbol, but nothing of that is meant. It's all perfectly innocent magic. So this is a graph, a complete graph on 5 vertices. Very good. Well, it's a drawing of a graph, no? In this case, it would just be V equal to say 1 up to 5, and in this case, E would just be the set of pairs of distinct elements. Or I could even add little loops, and then it will really be all of V cross V. Arrows in both directions, and so forth. All right, so that's a drawing of a graph. But what is a Cayley graph for a group and a set A? Well, the set of vertices is just a set of elements of G. And what is a set of edges? Or to be very concrete, I have one dot for every element of the group. And when do I draw an arrow from an element of the group to another element of the group? I draw another arrow from G, an element of the group, to another element of the group, precisely when that other element is of the form A times G, for some element A of big EA. Right. So I have a lot of arrows. So for every vertex G and every element A of big A, I have an arrow going from G to A times G. And I leave it to you as an exercise. At this point, if you prefer, you can stop listening and do the exercise instead. That this is a connected graph. No, a connected graph is one in which there is always a path from any vertex to every other vertex. It's connected in a sense. It's a network, if you prefer, that is connected. And why is that? Because A generates G. So using the fact that A generates G, you can prove easily, in fact, that the graph is connected. The KD graph is connected. Okay. Well, I define it formally as in the following way, that there is a path from every vertex to every other vertex. But what is a path? A path, again, is a drawing of something formal. It's when I have a sequence V0, V1, V2 up to Vk. So I'm connecting V0 and Vk. And the thing is, I have an arrow, so an element of E, an arrow going from V0 to V1, that is the ordered pair V0, V1 is in E, and an arrow from V1 to V2, and so forth. Okay, and the length of this path is just k, the number of edges. No, so it's as if every edge has had length 1 by definition. Now, and of course, it's nicer in many cases when our paths are short, that is, when they have few edges, no? So when the length is small. So, but that's not always going to be the case in every graph. And so we can define the distance between two vertices to be the length of the shortest path between them. No? So say in a city, this would not be the distance as the crow flies, but rather say the distance by public transportation. You find the shortest way from point A to point B, and that would be defined to be the distance. It's say the distance will be say 50 minutes because the shortest way is to take the bus and then the subway, and then you are there. Now, and the diameter of a graph is the maximum of the distance over all pairs of points. So you take the two points in the city that are farthest away in terms of, say, transportation. That will be my graph, the transportation graph, and that distance, that worst case distance, so distance for the furthest apart pair of points, that will be defined to be the diameter of the graph. So it's nice when graphs have small diameter. I give the example of a communication network or a transportation network, and that's not actually a very fake example at all. In pure math, it's really more of an example that we give to be understood. And many applications have nothing to do with transportation or communication networks. But in fact, if we go to expander graphs, which we will talk about later, the first definitions of expander graphs appeared in applied math journals on communication networks. So it's completely legitimate to think of these as being, literal graphs of a metro system or a bus system or a communication network, if you prefer. All right. So exercise. So the diameter of a Cayley graph equals the smallest k, such that every element of G can be written as a product of lengths at most k of elements of A. Yeah, so you know that, that was a definition of generating, that you can always, remember that you can always write G as a product of elements of A or A inverse. And I'm just saying, if you find the shortest word that works in each case, and the smallest k, such that words of length k or most or less, words of length k or less always work. You can always find a word of length k or less to express any element of G. That is your diameter, the diameter of your Cayley graph. It's not the definition. The definition is what I gave here. It's a definition that works for every graph. But if you apply it for a Cayley graph, it's an easy exercise to show that it's exactly this here. All right, and here, well, some of you may have noticed that here I had A union A inverse, and here I have just A. But from now on, we will assume that A equals A inverse, or what is the same. If I include an element in A, I will also include its inverse in A. That simplifies our life in many ways. For one thing, that means that our Cayley graphs will be symmetric. That is, I don't need to draw arrows, or if you prefer, it's like those old-fashioned signs you used to see in some cities. I do not know whether, well, we have people listening from all over the world, but in some cities you have arrows that show you that you're allowed to go on the street in both directions. That it's not a one-way street. So it's like this. It's with a Cayley graph that is symmetric. So if A contains all inverses of A, then every edge becomes a two-way edge. All right. Now, all of these definitions are completely standard. Just to simplify statements, I will introduce some notation that is also pretty standard, and one thing that is not so standard but simplifies notation. So when I write bars around A, I just mean the number of elements of my set A. Some people prefer to write number sign A. That's also fine. When I write A to the K, I mean precisely the set of all products of K elements of A. And this is slightly non-standard, but I think it will do. When I write the diameter of G, really the diameter is always defined for a pair, G and A. Here I do mean the worst case diameter. I find the very worst set of generators. So the devil, not us, chooses a set of generators. And that would be the diameter of G with respect to that devilish set of generators. That would be the diameter of my group. Now, I should say, for a group, it could be that this worst case diameter with generators chosen by the devil is very large. Let me give you an example of a group with a very large set of generators. I have some space. I don't have a lot of space. Let me do this. That is something you cannot do on a blackboard. So let me move the conjecture here so that I can draw a little graph. I will draw a cyclic graph, a big cycle. So if G, so this is an example. Say G is cyclic, say Z mod NZ. Then what will be the worst case symmetric set, generating set? So A could consist of just the elements 1 and -1. In fact, just 1 would be a generating set, but we want something symmetric. So this is a generating set because you can write any number as a sum of ones. Any positive number as a sum of ones. Negative number, you can add -1s. But then what does a Cayley graph look like? The Cayley graph will just join 0 to 1 and -1, 1 to 0 and to 2, 3 to, so 2 to 1 to 3, -2 to -1, -3, and so forth. Okay, and eventually this loop closes. So what I have is a huge cycle, and that has huge diameter, because the diameter here will be integer part of n over 2. You know, if you take you take this huge loop, this huge cycle, and you take two opposite points, There's only basically two paths from one to the other, and they are both very long, either this way or that way. So it's a case of huge diameter for n large. The diameter is proportional to n. That's what you should think of as huge. Because it turns out that when your group, so this is a case of a cyclic group, and abelian groups in general often have bad generators chosen by the devil, meaning generators for which the diameter is very large. However, the point is, people started to suspect in the 80s at the latest that this was not the case for all groups, that this was not the case, say, for the symmetric group. And then Bamai had a much more general conjecture that in general, if G is finite, simple, meaning it has no normal subgroups, and non-abelian, um, then the diameter of G, even for generators chosen by the devil, is always small. It's always bounded by log of the number of elements of G raised to a constant C, a universal constant C. So this has been proved for several kinds of groups, many kinds of groups. So I proved the case of G being SL2 of FP, meaning back when I was a postdoc. This means 2 by 2 matrices whose entries are in the finite field FP, or what is the same Z modulo PZ. So the entries, I mean, these are finite groups, so the entries should not be thought of as real or numbers or integers, not quite. They are integers modulo P, say, a prime P. And then, right, and this was generalized by two people who were students at the time, and Value stayed in math and had done some very good things. Then the next big generalization was to SL3, 3 by 3 matrices. That was already quite hard and required developing some more general tools. But there were several further generalizations. And this was eventually, there's this very nice, very general generalization by Piber Sabo and Briar Pintao, who proved that this, it was still basically, morally speaking, the same proof, or at least 2/3 of it were basically the same proof as in SL3 at least. But there were things that were not there as well. Otherwise, I would have done it. I mean, but these are two proofs that are in spirit very close to each other. It's simply because it's one of those cases where, it's on the, in retrospect, it's very natural. So they managed to extend these proofs to all groups of Lie type of bounded rank. Though, and this is important, we see, depending on the rank, people still believe Babai's conjecture is true with C an absolute constant. But it was proved back in the day with C depending on the rank. And we will later see how badly it depends on the rank and why. Now, I should tell you, okay, so actually I saw that there was a really nice summary to prepare people on simple groups. Thank you, Bogdan. On simple groups, why would we care about simple groups? Why do we care about these groups here and those groups there? So no, but not everybody read that summary, I imagine. So let me tell you. I said normal before. So when and simple, a simple group. So a normal group is one. A normal subgroup of a group is a group invariant under conjugation. And a simple group is one that has no non-trivial normal subgroups. Why do we care about simple groups? Because they are, in some sense, the atoms of groups, of finite groups. So you can decompose a group into finite groups. No? You may have normal subgroups, but that allows you to decompose, in some sense, your group into two groups, the normal subgroup and the quotient. And in the end, questions on diameter and growth essentially reduce to questions over simple groups. That for a long time has been some sort of moral principle, but now you can actually prove some very nice results in that direction. So there is a recent preprint by Sean Eberhard and his collaborators that I just got yesterday, in fact, though he had told me he would have something like that, where you really have some very strong result of that kind, where if you prove things for all simple groups, diameter bounds, then you also have diameter bounds for other more general, not necessarily simple groups. of a very broad kind. But well, I said depending on the rank, and then I will. So what happens? Let me actually draw another picture since I've already shifted things around a bit. It's a picture I like to draw. So the classification. So we will not use the classification theorem as such in this talk, but it should give the motivation. So the classification of finite simple groups. This is, you may have, I think you have all heard of it, perhaps. It's that epic theorem where the first proof was not all in one place, but if it had been in one place, it would have been the size of an encyclopedia. And nowadays it has been reduced to about 3 volumes, so they are not self-contained, and so forth. So it's a frightening theorem in terms of its length, and it really feels a bit like zoology, because it tells you that there are only some, with a lot of arguments, different arguments. It tells you that there are basically 3 kinds of groups, of finite simple groups. So there are matrix groups, so groups of Lie type, which you can think of as, we will go into more detail in a moment, but you can think of them as being matrix groups. No, you can multiply matrices, you can invert matrices, so you have a group. Finite groups if the entries are members of finite field. Then you also have Olten, or what is almost the same, Siemens. Well, Siemens is not quite trivial. Sorry, it's not quite normal. It has a normal, not quite simple. It has a normal subgroup, Olten. Olten is half of Siemens, the so-called even permutations. But what is Siemens? It's the permutations of n elements. No, that's a group because you can multiply 2 permutations simply by composing them. And then you have even the groups of Lie type include some decidedly fruity matrix groups. We will go over them in a moment, but there are some things that are far more horrible than groups of Lie type and Alt N. So you may have heard of the monster, no? Okay, so this is monsters. Well, there's one monster, one very big monster in particular. It's called the monster group, but there's only finitely many of them. So for asymptotic statements, we just care about for some constant and so forth. We don't have to consider the monster. We basically have one of these cases. All right. So before I go into the symmetric group, let me tell you. So what is of Lie type? As I said, they are basically matrix groups. So you have the classical Lie groups just over finite fields, not over R or over C. So that would be things like that would be SLN over FQ, SON over FQ, SP to N over FQ. Okay? And then you have other more exotic, well, slightly exotic. Let's not say exotic, let's just say exceptional Lie groups. They are called exceptional. There are infinitely many of them, but there are finally many types of them. Well, there are finally many types of Lie groups in general, but they are their own thing. And then you have really more exotic companions. They are still of Lie type, but you have Steinberg groups, you have Suzuki groups, and so forth. And what is the rank? I said bounded rank. Well, to keep things simple, the rank of a group, all of our matrix groups are contained in SLN, meaning the group of matrices that are n by n that have determinant 1. So the rank will always be less than that. Is that okay? So to be a bit more precise, let me give you a few examples. The rank of SLN is n minus 1. The rank of SO2n being orthogonal, it's a special orthogonal group. It's orthogonal matrices. That is n. The rank of SO2n plus 1 is n, and so forth. And all of those diameter bounds that they have given you here, that is special cases of Babai, all of them are based on the following. Results of this type. And my result back in 2005 was already of this type. So let G be a group of Lie type of bounded rank. Let A be a subset of G generating G. Then the result tells you, gives you an either or. Either, and this is the easy case, A is very big compared to G. It fills up a big chunk of G, and in that case, it's not so hard to show. Though elegant proofs were a bit later than 2005, it's not so hard to show that A cubed equals G. But also, it could be the case that A cubed is not greater than A plus, sorry. It could be the case that A is not large, and then what I'm saying is that A cubed is forced to be much larger than A. Until A is very large and covers almost all of G, and it only in 3 more paths you will get all of it. Until that passes, you will always have that A times A times A, what I write as A cubed here, is greater than or equal to the number of elements of A to the 1 plus delta. And then you can see what happens. If you can apply this result to A, you can apply this result to A cubed, to A to the 9s, to the A to the 27s, and so forth. So corollary, A to the 3 to the m, say. Okay, so you already see what we can do. This is growing quasi-exponentially, so to speak. And this is what gives you the diameter bounds. Okay. I also mentioned expansion in the title. I'm not going to go so much into expansion unless people want me to, but I think it's a really important concept and it's important as a motivation. So, in the last bit of the talk, we will see some ideas of proofs, and that's important. But I think background is also very important. What are good things good for? And that's sometimes one of the things we get. We really benefit from listening to a talk because we get a broader perspective. So being an expander, expansion is a property of graphs, or if you prefer, of families of graphs. If we are talking about an individual graph, we should talk of a delta expander, and something that is an expander for a given parameter delta greater than 0. And being an expander is stronger than having small diameter. Every expander graph has small diameter. So there is the combinatorial definition, the spectral definition, and the probabilistic interpretation, which you can turn into a definition. Should I spend a couple of minutes on this? I think so,
Yeah.
right? So the combinatorial definition, let me give you the ideas of the definitions. Okay, so the combinatorial definition will be that let me give you a definition. Every subset of the set of vertices that is, say, less than half so every subset that is not empty, that contains no more than half of the elements of V, has boundary, has a large boundary. Now here you already you already see it, there's this delta here, and I should add it, because when we speak of an expander family, when all graphs in that family are delta expanders for some fixed delta. If we speak of an individual graph, we should really say delta expander. So if you prefer, this is a graph that is hard to sabotage. If you have a communication network, and I think part of the idea, part of the idea of diameter, as I said, comes from communication networks, even if the applications nowadays are very different. Say if I have a subset here, right? Then the diameter here, the boundary here for S will be actually quite small. right? So yeah, so we don't actually want that. We want that there exists a delta, say 0.01 or what have you, such that the boundary of any large set is also large. Okay, there is a spectral definition, which will look a lot more sophisticated, but in fact, it's very intuitive, and we will see how the probabilistic interpretation, which is actually very close to it, makes sense. So for gamma symmetric and our graph is symmetric, for gamma symmetric, I will have the adjacency operator. So for an operator is something linear that turns functions into other functions. So when given a function f, the adjacency operator turns it into another function, add f. Yes, so this has spectrum. So because gamma is symmetric, sorry, but let me first define adjacency of f and then the adjacency operator. So it's a new function. And its value at v is just a sum of f of w over all neighbors of v. And so because I said that our graph is symmetric, our arrows are all both ways. But then my adjacency operator is a symmetric linear operator, a real symmetric linear operator. And what can people tell me about a real symmetric linear operator? This is a very important fact of life. And I know there are undergrads in the audience, and there's this odd thing that when you are an undergrad, you are taught linear algebra before all other things. Or sometimes you learn it in school, and then that means that you don't learn often. You don't always learn some really important things about them because you don't revisit that subject until you're in grad school sometimes. So a very important fact is that if you have a real symmetric matrix, then it has full real spectrum. No, if it's an n by n matrix, then it will have n real eigenvalues and n eigenvectors corresponding to them, all of which will be orthogonal to each other. Okay, and that's the case here. So you have these beautiful eigenvalues, which are all real. And d is the degree of the graph. So how many vertices come out, or how many edges come out of each vertex, which for a Cayley graph is equal to the size of A. So if you have that lambda n minus 1 is less than or equal to d minus delta. Gamma is an expander if it has a spectral gap. No, you can talk about spectral gaps in more general context for infinite groups or other operators, but for us in these Cayley graphs of finite groups, a spectral gap, delta expansion and a spectral gap are synonymous. But why do we care? Well, we care about linear operators for many reasons, but one of them is that you can actually derive quite easily from these two definitions are equivalent in a non-trivial way. It's really not to show that spectral expansion implies a combinatorial definition. That's relatively easy, but to show it the other way is hard. The proof is not very long, but it took a long while to find. Now, there is this probabilistic interpretation that you can prove much more easily from the spectral definition than from the combinatorial definition. So let's say you have a graph, not the satanic graph, because that is complete, so everything becomes too easy. right? And you have here a very tired or drunken, perhaps, mathematician. Let's say drunken to keep, no, it's a great tragedy for the mathematician, but fortunately, he or she is imaginary. So this mathematician can get drunk and nobody gets hurt. So this drunk mathematician starts taking a random walk on this graph. And if you're taking a random walk on an expander graph, you will get that very quickly you are completely lost. The probability that you are in any place of the graph is about the same. How quickly? About the number of steps should be about logarithm of the number of elements of the group. That's small. Logarithm of the number of vertices in the graph. So a short random walk equidistributes quickly. Right. And why do I mention expanded graphs? Because it was actually the first application of my growth result, other than diameters, which is already in the paper. And so Burgard and Gambord showed something non-trivial. I mean, it's more than non-trivial. It was a really nice result that got published in the same issue of the Annals as my result, but using my result. So not using directly the diameter result, but using this growth result. They proved that if you know, you have to dope sort of that result with other ones that existed, and you get that in many cases, you're going to be able to get, you get these families. They're not worst case, so it's not, they didn't prove it for all possible generators A, but they did prove that for A, a fixed set of matrices SL to Z, these are risky dense. Let me technically correct. There exists an absolute constant such that all of these graphs are delta expansion. And that was big progress because, for instance, in this case, it was not known for this of the following family. It's a famous family because people were frustrated. So this is a group. Okay. So just for that very simple family, so you're varying Q or P if you prefer, and you're letting A be fixed. So really A mod P is varying, but only because you're projecting these matrices modulo different primes. And then in this case, it's known, thanks to their work, which is based on my work, that all of these graphs are delta expanders for some fixed delta. Okay. And since then, there have been, I mean, there is a machine, they in part set up by themselves. So that if you have a gross result, you can use that as part of the fuel to get to these results. All right. So what remains to be done? Well, for one thing, let me go back. So groups of Lie type are not in such a terrible shape. They are, if you don't care about the dependence on the rank, they are in very good shape, and they have been for a while. So, we will care about the dependence on the rank. The monsters we don't care about because we're aiming at asymptotic statements. All 10 we do care about. I care a lot about permutations of n elements. I mean, I care about permutation groups. Say a Rubik's Cube is a permutation group. In fact, any puzzle of that kind is a permutation group. So it's very easy to grasp what is a permutation group. What the diameter is. In the case of the Cayley graph of the Rubik's Cube, that's, what was it? I forget, 26. So you can solve every position of the Rubik's Cube in 26 steps. Maybe it's something else, but say it's 26. And 26 is the diameter of that Cayley graph. In fact, permutation groups have a lot more serious applications. The first time they were really defined and studied in detail was by Galois when he was studying, well, he was developing what we call Galois theory. But let's go back to this. What do we have? That you should think of Semen, this is not the last time I say it, you should think of Semen as a creature made out of pure rank. In fact, some people like to think of Semen as being GLN over the field with one element. The field with one element is this mystical thing that doesn't really exist as such. There is no literal field with one element. But you can either give other definitions where it's a quasi-field or a hyperfield, rather, or sometimes there are people who don't define the field with one element as such, but they define objects over the field with one element. At any rate, if you have the merit of all of these results, it's that there is the delta. All of these results do not depend on P. They are completely uniform on P, and on A, but in particular completely uniform on P. In the case of cement, there is no P. It's as if there were still a group like ELN or SLN, but there were no P surviving. And yet, just hoping for an analog of these results would be meaningless. It would be an empty result, because all that a result can tell you in G is precisely the dependence on the quote-unquote rank. But nevertheless, we managed. So Sheresh passed away soon after this paper was finished, but Sheresh and I proved a while back that you can give very good bounds on the diameter of G. So there is still some dependence on N. We're not quite at the level of a Weiss conjecture, but it's a weak dependence. It's a power of log. Okay. Now the issue is that, as I said, you can. I don't need to refine the rank. You should think the rank as being bounded by N, and if you prefer, basically N. Okay. So how good were the results that existed before in terms of the dependence on the rank? Again, if you don't like the word rank, you can just think of the side N of a matrix. Well, people knew, so because of what the things that they generalized, people knew that the diameter of G was bounded by some power of log G, where the constant depends on the rank. Mind you, that has to be the case for anything that is closely based on results and growth of sets in groups. Because here, we believe that the Babai's conjecture is true without the dependence on the rank. But in the case of these triple product results, delta has to depend on the rank. There are counterexamples that show that this will be false if you chose a delta that should be valid for all groups. So people knew this with the exponent depending on the rank. The problem is that the dependence on the rank was pretty terrible. So if in Pieper-Sabo, the dependence was a tower of exponentials. So e to the e to the e to the e to the power e to the power e to the power e, or if you prefer 4 to the power 4 to the power, it doesn't matter. But the point is that the length of the height of the tower depended on the rank. So just imagine. Yeah. Whereas in the other generalizations here was not even given. But if you interpret it very generously, then you will end up with a dependence like this. And the question is whether we can do better. And yes, you can do better. In fact, we get an exponent that is polynomial on R, which is pretty good. You couldn't do better than linear on R. It's even a reasonable constant here. No, you couldn't do better than linear on R while still basing your results on triple product theorems. That's what I mean. Yeah, we do believe that there should be no dependence here. And this is still weaker in a sense than the result for Cmen, because in Cmen, what you have in the exponent yeah, so in Siemens, what you have in the exponent is you should think of this n as r, basically. So you have in the exponent is a logarithm cubed, basically, whereas here you have the rank itself, not its logarithm, raised to the first power. Exactly. Ta-da. So that's what we have got. And I can give you some ideas of the proof. I was told not to make things too technical, but I can think I can get some ideas through and give you some guidance as to what's going on. So there's a fact that all proofs for group of Lie type are based on so-called dimensional estimates. or sometimes called Larsen-Pink estimates. So Larsen-Pink did not know that they were working on a slightly different problem. For them, A was a subgroup, not a subset. Yeah. The issue is the following: that a set A can do one of two things. Either it can grow a lot. We eventually show that every set is like that, but say either A grows a lot when you multiply it by itself, and then we are done. Or if it doesn't grow a lot, it has to be really nice. So a set A that doesn't, the way to show part of the strategy towards showing that every set A grows quickly is to show that sets A that grow slowly are very nice. And we will eventually use the information to show they do not exist. So what does very nice mean? It means that if you think of my group as existing, say, in three-dimensional space, which for SL2 it's literally true, then I claim that I have my group is something solid, and when I intersect it with a plane, or you should think of my set A as something solid. So G is my space, my set A is here. And if I intersect it with something one-dimensional, then I claim that unless A grows a lot, in which case we are done, then the intersection of A with my one-dimensional thing should be bounded by about its volume to the power 1/3. So it's cube root of the volume. No matter whether I stick it here or here, there is no line on which my set A is too concentrated. Ditto with a plane. If I intersect my set with a plane or any other two-dimensional variety, I will get a slice that is not much larger than it should be. And what does that mean? So in general, I can say the intersection, even dropping the gross condition, intersection is always bounded by A to a certain power. So products of a few elements of A, you take the size of that and you raise it to a quotient of dimensions, the dimension of V, in this case 2, divided by the dimension of G, which is 3. So the intersection of my cup with a plane should be bounded by its volume to the power 2/3, morally speaking. Yeah, and as I said, results of this kind were known for groups, and I was proving, without knowing that, proving that for sets, but SL2, SLN, etc. And then this got absorbed into model theories, or works by Khrushchevsky and Pillai, which are actually very beautiful. Not that I understand that language completely. And then these were fed back by different ways into work by Pires, Bria, Grintao. Okay. But then the question becomes, how do these constants C1 and C2 depend on the rank, on the degree of the variety? In this case, I have just the degree here. It's a plane, so its degree it's one. But I could try intersecting my cup with some sort of paraboloid, right? And then the degree is 2. This is more complicated, so I expect the result to be a bit messier, but not much more. And the dimensional fee. So there should be a dependence there. How good is the dependence? Also, there's what's called the pivoting argument. We will not go into details, if to tell you that it's something that, I mean, it was, yeah, in its really mature form. I mean, it was there in a way before in my work and before that in work on the sum product theorem, but in its really mature form, it's there in the work of Pires, Bria, Quintao. And so you have the one thing you should get from this, other than the fact that that also needs to be optimized, is that induction is not true just for you can use induction over the natural numbers. Many of you must have done transfinite induction, really fancy induction, but always with an ordering. And one thing to take home is that induction does not really require an ordering. You can do induction on a group that doesn't have a natural ordering. It has something a bit more primitive than an ordering that is given precisely by a set A generating it. No? And there you have some notion of ordering in the process, but it's not really an ordering of the group, yet you can still do induction. All right. So I have negative time to tell you everything that we improved and further perspectives. So we can leave that for questions, or I can tell you very quickly what the areas of improvements were. So one of them was that I wish, so again, this is something that you can all take home. So when I finished my undergraduate degree, I had no idea of what algebraic geometry was. Some people had mentioned a guy, Grothendieck, who was allegedly crazy and not very nice to some of his friends. That was probably just corridor noises. That's very abstract. So when I went to grad school, like most people, I tried to read Hartshorne, and I was slightly traumatized. But I wish somebody had told me to read Mumford's Red Book instead. So no, I don't have no ties to Mumford. I'm not getting any proceeds on sales of the Red Book. You can download it. It's a very old book. Download it for free somewhere. But you know, chapter 1 already has many of the tools you need for all of these. And the question is how to make chapter 1 explicit in a, or at least make the dependencies clear in an efficient way. And that's not so simple. But it's very concrete algebraic geometry. You don't really need schemes for this. In some ways, it's a bit like 19th century algebraic geometry. And also there's a notion of escape. And let me give you the notion of escape and wrap things up. So what is escape? Escape is the following. So you have a group acting on affine space. So in dimensional space, you have a variety in space. It could be a plane. And I have a point that is a prisoner in my variety. So this is my point that is a prisoner in my variety, right? Yeah, you're looking at the video. You're not just looking at the slides. So I have my point, but you can also imagine, because of what I'm saying, a point that is in my variety, and I have a group that is acting on the variety. And the issue is that if I'm given that there is a way by several elements of the A that are acting here, being elements of the group, if there's a way for my point to escape from the variety, then there is a short way. How short? Well, the length depends only, in a very good way, on the degree and dimension of the variety. And there were results of that kind, but they can be improved. And we had different ways to improve them, and that was important. And also we improved the inductive procedure. Yeah, and there are also ways to generalize escape, the notion of escape. So one way that I like to explain this, and this will be my last slide, is that you shouldn't just think of the problem of optimizing the result that I told you, that given a point and given a variety and given an action, how to find a short way to escape. You should think of something stronger. So remember the legend of Theseus and Ariadne. So Theseus goes into the labyrinth to kill the Minotaur, but Theseus is very brave, but not necessarily that smart. So Ariadne, who is the one who really has the inside information, tells him, okay, Theseus, you go kill the Minotaur, but I'm giving you a set of instructions, a recipe book, if you wish. And no matter how lost you get inside the labyrinth, one of these short recipes, one of these short sets of instructions, and there, one of these short, is a short recipe book containing a short list of short sequences of instructions. One of those, no matter where you are in the labyrinth, one of these lists of instructions will get you out of the labyrinth. So that will be that's a stronger kind of escape, where you're not just bounding better the number of steps, but changing, generalizing, making stronger what you mean by escape. And I could tell you many other things, but I think I better finish here.
Okay, yeah, thank you for your talk. So now I will allow everybody to unmute yourself if you prefer. So you can now unmute yourself and ask questions if you in voice, if you like, Or if you prefer to write in chat, you can ask in chat. So anybody, if you have any questions, please ask. I think I will start with my question. Maybe somebody will join. So in Babai conjecture, there is this constant C. So are there any kind of numerical experiments and whatever which gives an idea where the conjecture is true, and if true, which constant C to expect?
Yeah.
For
Well,
example, in permutation groups, yes, it's just one
yes.
parameter n, and we can just compute this diameter for various n and take logarithm and then see what C can be and anything.
Yeah. We know that C cannot be smaller than 2. But as far as we know, I think C might be 2. This it has not been disproved. And experiments don't seem, people have not been doing enough experiments, but but also with experiments, it's hard to rule out something really nasty and pathological. There could be a very weak example with a C greater than 2. But up to now, we don't have any examples or even a strong suspicion that C could have to be bigger than 2. Maybe let's give us a bit of room to plus epsilon. So if somebody comes up with a set of generators A such that the diameter, the C needs to be 3, that would already be major progress. Well, anti-progress, but progress.
Okay, maybe it should be some constant before, yeah, because if you just formulate conjecture log n to the power of C, maybe
Yeah.
it's like
So
it's
but
yeah.
C could be 2. C could be 2 for all that we know.
Yeah, even without constant before, it's O of
Oh,
log,
okay. You are
because
completely right. Let's
otherwise
let's
it's
let's allow two absolute constants. Okay, C0.
yeah.
Yeah, so some absolute constant, C0. You are completely right. I got it out to simplify matters, and it was correct. But now we are talking about what C should be. Let's allow C0. So C0 is a constant. We don't care that much about what it is. But if you allow if C0 might be a trillion or a Google, but big C, if you allow that, big C could be as small as 2. Yes. Might be. I'm not going to bet either way. I don't have strong reasons to have a belief in either direction.
Okay, so is it possible to explain in simple terms when this C log n in the exponent comes from, and what is the main bottleneck to make it polynomial? Why we have this
Yes.
logarithm then?
So the logarithms here.
In the exponent in your proof, yes.
Yes, so
Yeah,
this is
that
already
one.
better than polynomial. So this is, in fact, I should emphasize what we have proved here. So what we have managed to prove, this is a former postdoc, a former student, Daniele Donna, and myself. What we managed to prove was polynomial dependence, but even though this is much better than what people used to have, this is still not as good as what my result over Siemens was. So in Siemens, we're still far more advanced than for matrix groups. So there are really two different questions. What are the bottlenecks if we try to improve the result over symmetric groups? And what are the bottlenecks if we try to improve to prove, prove Babay's conjecture for matrix groups, or at least, and this is already a very hard problem, at least make the results for matrix groups as good as the results for the symmetric group. These are two different questions. Which one should I answer first?
Whatever you prefer.
Okay, for the symmetric group, I should say I really don't know. I'm a bit stuck. I've been trying many things, but I believe that something that should yield some progress is that, as I mentioned, SLN can be seen as a matrix group over the field with one element, this mystical thing. But there are different theories of the field with one element, but one that I really like, though it's compatible with some other theories, is what Matthew Baker and Lorscheid and their collaborators have been doing. I think that's quite appealing. And I think one sign of a good theory there is that their theory has implications that they didn't see at first, even fairly simple implications. But the point is that the moment you start seeing Siemens as a matrix group over the field with one element, you can define varieties. And they define varieties. And I think it's a notion of variety that doesn't seem very intuitive, but then it starts making a lot of sense. And I haven't, to be honest, come up with new arguments for the symmetric group yet using that theory. But it turns out that some classic arguments that are very useful for growth in cement can be expressed in a very natural way. Say, Baba splitting lemma, it can be expressed in a very natural way once you use the theory of the field with one element. And then it becomes a bit complicated depending when you go beyond linear varieties. It's clear what a linear subvariety of the symmetric group should be. Well, it wasn't clear to me, but it's clear to me now because we've seen the light with this theology of the field with one element. But then what should be varieties of higher degree? I think there's a reasonable interpretation there that is suitable for the purpose. So maybe I think that that's something that really merits further exploration, and maybe that will yield improvements here. What I'm more hopeful for, though it's still to be done, is that will yield progress here. That really developing the theory of growth in cement with the language of the field with one element will cast further light on which arguments for cement can be transferred to matrix groups. So
okay, yeah, thank you for this. Can you just press on chat button in the top? You see in the top of Teams, then we press share, and on the other side there is a chat button. I just want you to see yourself the question. It's a question from Ismail.
I'm not seeing the chat. Where is the chat?
Yeah. At the top, there are various buttons like share screen, microphone, camera, and then in this list on the left,
yes,
there
I
is
see
a
chat. It's just that I'm not seeing the questions that people are asking.
Yeah. If you press to this chart, you can see the chart actually.
Yeah, the problem is that I can show I'm not seeing the questions.
Okay, Ismail asked, if you don't see, I will read. Thank you for the lovely overview. Besides improving the constancy R, what are the big open themes, questions, threads? Does the complete zoology of final group limit future research? Does the complete zoology of finite groups limit future research? Does this field have any interesting connections to physics or machine learning? That's a question from Ismail.
Yes. Yeah, I would say the following, that there's still a lot of, even if people manage to prove Baba's conjecture, there would still be the question of expansion. And I don't think we should feel limited. I mean, there will be a lot to learn, even once Baba's conjecture. I don't think Baba's conjecture is going to be proved very soon. So there's a lot of work left to do. But there's a lot of things to be done on expansion. Even in SL2 over FP, so in 2x2 matrices, there are open questions on expansion, such as, for instance, whether the family of all Cayley graphs of SL2FP for all possible sets of generators is an expander family. There's experimental evidence that it is, but we don't know that. And there are people doing some very interesting things with machine learning. In fact, I have a friend who keeps telling me, there are some people using machine learning to study these questions and questions like them. I know that this might strike some applied people as applying things in the wrong direction. Maybe the question was more about applying expansion to machine learning and not applying machine learning to questions in groups. But I know more about, so I've been hearing, so I mean, I would have to look in my emails, but one moment. So people keep telling me. So yeah, Alexander Chervov keeps trying to get me interested in this, and I think he's doing some very interesting stuff. Yes, some very you can look up his preprints. Yes, so there are questions that are being attacked by means of AI/machine learning. Now, there are also applications of expansion itself to computer science. You can find, so I think one of the best introductions to application to expanded graphs in general is still the paper by Huri Lineal and one moment, leaving one person out. Yeah, Huri Lineal and Vigderson. They have a very nice article in the Bulletin of the American Mathematical Society from 2006, but it's still very current. And there they give lots of applications to computer science, and I'm sure there are more by now. Because after all, an expander in some sense is a good graph, a good network.
Okay, thank you. I think we need to stop here. We will run over 1 hour already. So thank you very much for your talk, and thank you everyone for participating.
Thank you for inviting me. Yes? Hi.